So today we start in the first part dealing with specification of spatial dependence, how to put spatial dependence into a regression model. I want to start by continuing our discussion of spatial weights, if you wish, by focusing on this concept of a spatial lag or a spatially lagged variable, which is really the way in which we bring space into the equation. Then I want to spend some time on the notion of spatial covariance, which is really a characteristic of the joint distribution of all the data, all the spatial data that we observe. And it's important to know the difference, or to appreciate the difference between spatial weights on the one hand and spatial covariance on the other hand, and how we get from one to the other. And then I want to spend a little bit of time just giving you a quick refresher of some notions of multivariate distributions. This may be very familiar to you, but it's very important in the spatial domain specifically to appreciate the difference between a joint distribution and a conditional distribution. Because as we'll see in the second part of today, there is a major difference between what we call simultaneous models, which are about a joint distribution, and conditional models, which are about conditional distribution. So let's start with the notion of a spatial lag, or a spatially lagged variable. And yesterday we saw the notion of a spatial weights matrix, which was a formal way to express which locations were neighboring each other. So we had this matrix which was of the dimensions of the data set, let's say n by n, whose elements w, I, j specified whether or not I and j were neighbors. If I and j are not neighbors, that would be 0. If they are neighbors, it would be non-zero. We talked a little bit about some basic notions where the weights start out as 0, 1, but that can be generalized into all kinds of values for the weights matrix. The basic thing is that if there are neighbors, it's non-zero. If they're not neighbors, it's 0. So then, with that in hand, we can construct a new variable. And the new variable is, in essence, a weighted average of the values observed at the neighboring locations. So we take the neighboring locations, which we specify through the elements of the weights matrix, the wij, and then we basically multiply a row of the weights matrix by the full vector of variables. Now, the full vector of variables is really overkill because, as we saw yesterday, there's only a few non-zero elements in a row of a weights matrix. If we look at the counties in the US, 31 some continental counties, in that row for any specific county, there are only 5 or 6 non-zero elements. Everything else is 0. So in essence, even though mathematically you express it as a weighted average of all the observations, because most of the weights are 0, in effect it's only a very local weighted average of the immediate neighbors, as expressed through the weights matrix.
What are the subscripts on Y, IL?
Okay, I is the I for the location. The L specifies the lag. So YIL is the spatially lagged variable for location I, which is constructed by multiplying each of the value of Y at each of the other locations by the corresponding weight in the weights matrix. So the row of the weights matrix W corresponding to location I would have WI1, I2, and so on, all the way to WIN. And each of these in a matrix multiplication gets multiplied by the matching observation for Y. So WI1 multiplies Y1, WI2 multiplies Y2, and so on. So if you think of the row of the weights matrix as a row vector, and you think of all the observations as a column vector, you multiply the matching observations and sum that up. So, but this is way too complicated relative to what it really is, because you really only multiply 4, 5, 6 neighbors. Everything else is 0, so it gets zeroed out. This spatially lagged variable is, in a sense, a smoother because it's a weighted average, so it reduces the variance. The variance of the spatial lag is smaller than the variance of the original variable. One thing to keep in mind is if you're used to remote sensing manipulations, this is not a window average. Oftentimes you move a window over the data and compute an average or some other characteristic of the data, the observations in that window. This is not quite the same thing because, as we saw yesterday, the diagonal elements of the weights matrix, the self-neighbor type elements, are 0 by convention. So it's an average of the neighbors only. It doesn't include the variable itself. The traditional notion of a window average includes all the observations in the window, so that would include II, so to speak. But in this notion of a spatially lagged variable, because of the structure of the weights matrix, the diagonals are 0, so the observation itself is not included in the averaging. And this is another reason why I didn't really spend too much time on this yesterday, the notion of row standardizing a weights matrix, but this is a good reason to do that, because if you row standardize the weights matrix, then this operation is a simple average. If you do not row standardize the weights matrix, then you don't necessarily know what you're getting, because it depends on the values of the weights. If you keep the original 0, 1 weights, for example, then the spatial lag is not an average but a sum. Then you're simply adding up the neighboring observations. So as long as the number of neighbors is constant throughout, that's actually not a problem. But in practice, the number of neighbors is typically not constant. So then you're introducing scale differences. If some observations have 3 neighbors, you add up 3 observations. If they have 6 neighbors, you add up 6 observations. So there's a mismatch here in the scale. And that's a good reason to standardize it, row standardize it, so everything remains in the same scale.
In a real sense, you're reducing the local variance, and you're sacrificing some information, right?
Well, it is.
Might be of interest. Or
let me put it differently. The real motivation for using the spatially lagged variable is that there is no counterpart to a shift in time as there is in time series. In time series modeling, to deal with the correlation over time, you introduce a notion of a shift. So you have time t, then you shift by 1 period, that's t minus 1. And everybody knows what t minus 1 is. In space, especially in irregular space, that's not a clear notion. On a grid, you have north, south, east, west, but once you get into irregular spatial layouts, that's undefined. And so you cannot really use the counterpart from time series analysis, which says, well, I'm going to relate what happens at time t to what happens at t minus 1 or t minus 2. What we would like to do is relate what happens at location I to location I minus 1 and location I plus 1, but we don't know what that is. On an irregular spatial layout, that's undefined. On a regular one, and we'll see some examples later, on a line or on a grid, you can define that. But if you have an irregular layout, like I'll show you in a minute, it's not defined. So how do we relate then what happens at a location to what happens at other locations? And rather than using this notion of a shift, we use a notion which is closer to what in econometrics is called the distributed lag, which is really an averaging of observations, other observations. Typically it's used in time, but here it's used in space. So the key, the averaging is a no-brainer. The key is which observation do you average? And that is determined by the weights matrix. And so it is a reduction of information in some sense, but it is because we can't really use all the information on an irregular layout. So given that we have this concept now, we can just introduce some more notation, because we'll switch very quickly to mostly matrix notation because it's much more compact. So essentially, we have the lag at I as the sum over j being all the columns in the weights matrix, or all the potential neighbors, of the weights element, wij, times the matching yj. And in matrix notation, very compactly, this boils down to the multiplication of a matrix W, which is an n by n matrix, times an n by 1 column vector. So if you're a little rusty on matrix multiplications, n by n times an n by 1 gives you an n by 1. So you're back with a regular column vector, which you can then manipulate in the usual fashion. So you'll see this wy a lot from now on, and other forms like it. Now, as I mentioned yesterday, the W, even though we will refer to it as a spatial weights matrix, in fact, it's mostly consisting of zeros. So in practice, we will use it in a sparse form. We will not carry all the zeros around. So we have this new variable now, and we'll use this new variable in various regression specifications. Let me illustrate it to show you that it's very simple averaging. This is an example of land values. So we have the land value in the middle, and we have the 4 neighbors. What is the spatially lagged variable for lag value? It's the average of the neighboring lag values. So even though there may be 100 other counties in this data set, they don't come into play because their weights are 0. They're not neighbors. So it's simply a local averaging. And I have another example here. These are same thing, a county with 4 surrounding counties, and we'll make the spatially lagged variable. This is an example using GeoDa. It's actually, there's one like this in the workbook if you have a chance to look at this. And here you see what's happening. It's the variable on the very left, in the very left column, the value at that county. This is the classic data set from Noel Cressy's book dealing with SIDS death rates. So for that particular county, there actually aren't any. But then if you take the weighted average of the neighbors, which are the 2 on top and the 2 below, you end up with something like 1.19, which is highly non-zero. So then what we're going to do in our analyses, and what we actually did yesterday, but I didn't get into it, is we tried to get some kind of summary measure that relates the value at I, which is the 0 in this case, to the average of the neighboring locations, which is the 1.19. And specifically, the local measure of spatial autocorrelation, the local Moran's I, looks at the extent to which the relation between the value at I and the value, the average for the neighbors, is different from what one would expect under spatial randomness. And that is in essence what the local Moran is about. It's a comparison of the value at I with the weight, with its spatial lag, with the weighted average of the neighboring locations. Yeah.
In the example that you showed, you weighted with 4 counties equally, quarter each. Was that just a convenience? You could really use any weighting you'd like?
Yeah, the question is about the weighting of the neighboring counties, that in the example it's an equal weight, and is that a convention? It really, it isn't convention, but it's not the only convention. The equal weighting is by lack of other information. So essentially what you do is you start with, say, a contiguity matrix. In this case, we have 4 neighbors. So you have a weights matrix with 0s and 1s. The 1s are for the neighbors. You row standardize it, which makes each weight 1 over k, where k is the number of neighbors. So if you have 4 neighbors, the weight will be 1 over 4. And that's the most straightforward way to proceed. And in the absence of other information, it is really the only way to proceed. Now, if your particular problem, substantive problem, would suggest that the length of the border is relevant, or some combination of distance and length relative perimeter, or something else, then those form the basis for the weights. And then it's really depending on how you want to interpret the spatial lag, whether or not you row standardize. But in that case, they would not be equal weights. Okay. So there is one instance where it would not make sense to row standardize is where you use the weights as access measures. Say there's this notion of a potential, which is essentially a weighted sum of values divided by the distance from the origin to that particular location, say in marketing analysis or accessibility analysis, if you want to see how accessible is a given location to hospitals, say. So the hospitals are characterized by number of beds or square footage or number of doctors or something like that, and they're divided by the distance from your location to that hospital. So then the weighted average of this actually means something. And there is no real necessity to rescale that or restandardize it because you use this as a concept as such. So in that case, your spatially lagged variable would be the weighted sum of, say, your hospital beds or number of doctors divided by the distance from a given location to those hospitals. And that then can enter into a regression model. So anytime you have substantive reasons not to standardize, you shouldn't. In practice, in most cases, you don't have that. So then, to keep it simple and to keep it comparable, it's a good idea to row standardize. And unless you have a good reason to differentially weight the neighbors, you shouldn't. Because by differentially weighting the neighbors, you're introducing new structure in the model. And as we discussed yesterday, the more structure you introduce, the more you have a chance of introducing the wrong structure. And so in practice, I mean, this is not theoretically based, but in practice, it's a good idea to keep things simple, especially in the beginning, and to introduce the complexities later on. So say you start with a model with equal weighting, and then you find that somehow it's not satisfactory, then you would introduce some complexities to maybe change the weighting. Yeah.
GeoDa doesn't give you the option, does it? It just
No.
standardizes.
At this point, GeoDa does not give you the option to not row standardize. So GeoDa always row standardizes. Because GeoDa actually, in its current version, doesn't use the information on the weights. Even though you have distance-based weights and so-called general weights, they're reduced to 0, 1, and then row standardized.
Couldn't you get it in there by manipulating your data set before you put it in though?
You can, but GeoDa ignores it. So this is something that was fixed in the new version, which isn't out yet. But so even though you can read in a weights file with general weights in the third column, and we talked about this yesterday, Julia showed you some examples, GeoDa actually ignores those values and only incorporates them to the extent that they are non-zero.
But you could reweight your variables, your raw data variables.
You can do that, yeah. You can manipulate it on that end, but not in the weights end.
It'd be like transforming.
Yeah, right. Yeah, yeah, but that is definitely a limitation of the current version of GeoDa, and in the new one, it's actually, this is where it broke. This is what we changed, and then some of the other things were broken. But I believe, I'm pretty sure that in SPDEP, you can have general weights, and you can keep them general. You don't have to row standardize them. Because SPDEP has 3 different formats for the weights. And so you can actually, if you really insist on some different transformation, then I would say you should use SPDEP, as we'll see this afternoon in the lab. Okay, so with these spatially lagged variables in hand, we can then introduce them into the regression model. And so we can have spatially lagged explanatory variables, which we will express as Wx. You can have spatially lagged dependent variable, which we will use as Wy. And then you can have spatially lagged error terms, which we will use as W epsilon. The error terms are the disturbances in the regression model. So this is the most straightforward way to bring the spatial correlation into your regression specification. You basically add new variables that are weighted average of existing variables at neighboring locations. And the idea then is to model spatial autocorrelation by some linear relationship between the value observed at a given location and this weighted average of the neighboring locations. That's the principle behind the specifications. So with these spatially lagged variables in hand, we then have three broad classes of regression, spatial regression models. We've touched upon two of these yesterday, and we'll revisit them later today. The spatial lag model, where we bring WY, the spatially lagged dependent variable, in on the right-hand side. The spatial error model, where we bring W epsilon, the spatially lagged error term, in the part of the error, in the disturbance. And then a model that we'll talk less about, and I'll clarify in a minute why, is what is referred to as a spatial cross-regressive model, is when you bring spatially lagged explanatory variables, Wx, into the specification. The reason why we won't say much about it is that it doesn't really require specialized estimation techniques or test statistics, because the Wx, it is a spatial variable, but it's an exogenous variable, so it can be treated just like any other variable. It's a new variable, and it provides spatial information, but from a technical point of view, from a methodological point of view, you don't have to worry about it. You can treat it as any other additional variable, and this would be the case, say, if you are modeling some demand and you want to introduce an accessibility variable pertaining to another phenomenon, not the one that you're, not the Y, not the same dependent variable that you're interested in, but say you want to explain income in a particular area by employment in that area, but also employment in the surrounding counties. Okay, because people commute, they don't necessarily all work in the same county. So then the employment in the surrounding county would be a Wx variable. As we'll see later on today, it's actually not that simple, because there are connections between the structure of a spatial lag model and the presence of Wx variables. So then there are identification problems, in the sense that it becomes very difficult to disentangle the Wx that you want to put in separately from the Wx that is in there implicitly from the use of a Wy. And we'll go through these various permutations later on today. But it is perfectly legit to have a regular regression specification and to introduce a Wx as an additional variable. If that's all you do, there is no special methodology required. It gets more complicated when you also introduce a spatially lagged dependent variable in addition to the Wx, or some spatially lagged error terms in addition to the Wx. Then you get into an area where you have to really think carefully about identification and what your parameter actually means, and to what extent you can separate out the part of the coefficient that is due to Wx alone and is due to the interaction of Wx with these other variables. And that is not that straightforward. And we'll get into that later on today.